All right, all, good morning. Go ahead and get started with today's material. So what hopefully you see here is we're going to continue with that division that we started kind of looking at yesterday. Remember, the purpose of division is going to help us with factoring to find zeros of polynomials, right? Make sure, remember, as we talk about that, this is all kind of expanding that idea that, hey, we need to find x-intercepts when we talk about functions, right? Well, we're now bringing back the equation aspect of, hey, let's just find solutions in general. That's why we bring in the word zeros of the function. That means it can be real or complex, okay? But for polynomials, factoring is our focus because we know with the zero factor property, so if you have something like x minus a and x minus b, as long as it equals to 0, then your two solutions come from those factors, right? Polynomials, it doesn't matter how many factors we have, that's how we get to those solutions. So that's what we want to build upon. Now, there's many other reasons that you're going to need long division if you move forward in mathematics, but for one of the focuses right now for us is going to be on the polynomial functions themselves, okay? So the first problem here I wanted us to kind of work on was making sure we can deal with the long division itself. Now, I wrote the problem differently than I did yesterday. So the way I have it written here, what is the divisor? Right, so we need to make sure to see that as we deal with this, that even though I didn't write it the same way we did yesterday, my divisor is the x minus 1. Right, we're dividing into f of x. So when I go to set this up, we're putting x minus 1 on the outside and f of x on the inside. Where do I go from here? The key is the first terms, right? So our first time through, we're doing the first term divided by the first term. This is where the quotient rule helps us, as we kind of reviewed a little bit yesterday. Like, hey, if I have 3 x's in the top and 1 in the bottom, I can divide one pair out. Now the 4 just kind of follows along, but I should only have x squared left over. Okay, if you need to, write it out as such. Scratch out the bottom and subtract 1 from the top. Okay. We're not always going to divide by linears. I'm just kind of continuing from where we left off last time. So right now we need to multiply, right? So we divide and then we multiply. Now make sure you put that 4x squared over here though. As we talked about, put it over the negative 16x squared because they're like terms. But we do want to multiply with what was the divisor. The key there is that's where the distribution takes place. That's what brings in the minus 1 aspect of our divisor. So as I bring it over here, we can move on to what?
Make sure you change the
But the key is the subtraction, right? And the whole focus of that for polynomial long divisions is to make sure that these first terms go to what value? To 0, right? That's it's kind of like what we dealt with equations, right? That whole idea, we need that to cancel out. That is our focus, okay? But now we have to make sure to deal with the rest of that, right? So we're gonna have what, negative 12x squared? And what do I do now?
you bring down the 13.
All right, so we got to continue the division until we get through the entire polynomial, right? So this is where we say, hey, I can bring down my next term and do the whole process again. So this was step 1. Probably gonna have to do this possibly 3 times. Okay, so step 2 then says negative 12x squared divided by x, which is just negative 12x. This became our first term now, just like we saw the 4x cubed was. So we're seeing that continually same algorithm taking place. That's the nice thing about algorithms. Keep doing the same thing until we get the desired result. Our result is we can no longer take out the first term, right? And that would leave us with what we call the remainder. That's what we discussed yesterday. All right. Now be careful, this one, it is a negative. So when you're dealing with the subtraction, watch out how you handle your signs. right? But hopefully you'll see there that with that negative 12x in place, those first terms cancel the 0 again, and we can continue through this problem. Is there any questions with that second time I can help clear up for somebody? So we did it once, now we've done it twice. Are we done?
No.
We see an X and an X, right? So we can we can do this division one more time. Just so happens the division gives me 1 this time. 1 times anything is itself, so that's kind of nice. But what do we need to notice about this subtraction here when we're done? We got 2 things here, right? What's the first thing we should make sure we know how to identify? The quotient. Right now, I'll just put that as Q of X. All right, so that's our quotient. What's the other piece we have? A remainder, right? And that would be like an R of X, right? Now with that though, my question wasn't to identify the quotient and the remainder. We need to be able to identify. My question is X minus 1 a factor of f of X? Is 5 a factor of 21? Why not? Right. If I divide 5 into 21, we're going to get 4 times, but 4 times 5 is 20, right? So there's that 1 left over. We have a remainder of 1. The same thing is true for polynomials. Your remainder tells you a lot, that this remainder does not equal 0, right? So X minus 1 is not a factor of f, okay? Now, the way that we would write this would be looking with that division algorithm. So let's look at that after we finish with this. Are there any questions though before I go back to that division algorithm perspective? All right, so the division algorithm, that's this thing here. Don't need to have to rewrite the whole thing. The only thing I would technically change here, it's not just R, right? Most of the time it is just going to be a constant value because we're going to focus on that. But as I mentioned, I could have changed it to X squared minus 1. And we could have did the division with that perspective, okay? What you're going to find here, what that means is we're taking our function f of x, which as we saw here is the 4x cubed and we're doing the division with this. So what we want to say is that, hey, I took 4x cubed minus 16x squared plus 13x minus 3, and I divided by x minus 1 because that was our divisor. The quotient is the piece that we got from this, right? So we want to make sure to take that and bring it over here as well. That's the quotient. The remainder, as you see, I need to put that as that fraction. Remember, we kind of talked about mixed numbers yesterday? Like if you have 5 over 2, if I tried to do that division, I get 2 with 1 left over. I just reminded us that, hey, when you see that, that means 2 plus 1/2. All right, for polynomials, we have to put the plus sign. So that's what you're seeing here. Okay. With that in place, so what did we get? We got -2, right? So we'll put -2 over the x minus 1. All right, any questions where I'm getting this from as far as just rewriting the division in that, using the division algorithm? Now make sure you see here, I changed this sign because our remainder was -2 when we did all that. So make sure you go back here and like, hey, that was a -2. So instead of a plus sign, I used a minus sign for that -2.
What'd you say that formula was?
This is the division algorithm. It's just saying, hey, if you divide this, you should get a quotient and a remainder. It's us rewriting the division in that form of what we found. Now, the one thing I want to make sure to show here is how can we look at this from another perspective to see that it's not just multiplication when we're done, right? Well, this is where we can go in and say, hey, let's multiply everything by x minus 1. So let's take x minus 1 and multiply it to each piece of this, right? So I'm going to bring this down here. I'm going to shrink it down a little bit, and we're going to multiply everything by x minus 1. Now, with that said, make sure you see here, I need to put this whole thing in parentheses because that was my quotient, right? That whole thing was my quotient. The nice thing about this, though, is we solve from equations, right? Solving rational equations, those are gone. Those are gone. That's the nice thing about it. What you're going to find here is the reason I want to rewrite it this way is because this will just be f of x by itself now. That is my function. Okay. On the other side, though, we'll have x minus 1 times the 4x squared minus 12x plus 1. But what do I not want to forget about? That 2, right? I need to make sure to put that minus 2. Okay. So I changed my division to what operation?
But what happens to the x would be the,
Yeah, this is f of x,
so
remember?
you would just change it?
Yeah, I was just for the sake of making sure to point backwards, that don't forget that this was my function. Okay. I'm using that just to emphasize this is where we got it from. Okay. Now, to be factors, the only operation we can have outside parentheses is the multiplication, right? So this right here is multiplication. But that remainder tags along through what operation, right? In this case, it's subtraction. That's why this is not in a factored form. What would this remainder need to be for us to have factors? For this to go away completely, there's only one number that will work. No. A remainder equal to what? 0. If it's 0, I would not need to put anything there. If you don't put anything there, then all of a sudden, hey, look at that. That's factors. Okay, that's factors. That's not what we got here, though. And I just want to make sure to show this means that, hey, this is another way to write our function. Now, does that help us really? No, but that wasn't the point of the problem. The point of the problem was just tell me if it is a factor or not. So make sure you see here that when that remainder is not 0, you would say not a factor. Is that clear to everyone? Any questions or concerns? All right, so let's take that a little bit further then. That's what the next problem is doing here. Now, make sure you see here that, like, I'm putting a restriction on the remainder. As we saw just now, our remainder was -2, which means it's just a constant value, right? No matter what I plug in, I'm always going to get -2. So that's what I mean here, that R is a constant function. It's going to be a number that never changes, right? That means that we could treat this like a constant value. It's no longer going to have variables. So that's why I'm making a slight change, okay? So it's still my remainder, but make sure you see I took off the of x part, okay? Now, what I want us to see here is we can use this to help us do something a little bit more quickly with the division, all right? Now, when I go through this division, what you're going to see here is if I multiply all of these by that divisor again, just as we did on the previous problem, this one's just in more general terms rather than specific terms. We're always going to get the divisor times the quotient plus the remainder, okay? Now, we like this though, because at this point, this is something useful, right? If the remainder is 0, we have something that is in a factored form. If it's a factor of the function though, it also has significant meaning to us, right? So let's go into this situation. The reason we know this will be true whenever we do is we're going to force d of x to be x minus k. Right? So what is the 0 of d of x in at that point? Our divisor. Well, if we take the function and we set it equal to 0, we get x equal to k itself, right? Because a number minus itself is 0. Well, if that's what we're forcing here, what happens if I plug in 0 into our function? Okay, so if I'm forcing that to be true, I'm assuming this is true, okay? What is f of 0 then? Well, plug in 0 wherever we see an x, right? Do I need to worry about changing the r right now? As I said, it's a constant value, right? Is that clear to everyone? Now, the r of 0 was an ideal situation, but we could talk about that a little bit later, okay? But when I go through here, do we know what the function is if I didn't give it to you? Over here, I gave us function, right? But over here, I'm just saying this is general, so we don't know this, so we can't evaluate it, right? We just got to leave it alone. Do we know the quotient then? So can I tell us what q of 0 is? No, right? The remainder, we don't know that either. The only thing we know here is this d of x because I just said let it be this. Is that clear to everyone? Now, with that said, if I plug in that 0, and I totally wrote this wrong, y'all. Sorry. Not 0, we're supposed to be doing k. Change those zeros to k's. Again, make sure you see, though, that doesn't change anything. I just picked a different number other than 0. K is what we want, though. I don't know what f of k is because we don't have an f of x given to us to plug into. We don't know what q of k is because we didn't have the function to begin with to do the division. However, I define d of x to be x minus k. Is that clear to everyone? That this right here I just defined for this purpose. And I like that, though, because what is it going to be when I plug in k? What is a number minus itself? D of k equals k minus k, which is 0. Okay. With that said, moving forward, that would give us f of k equal to 0 times that quotient of k plus r. Well, what's 0 times anything? Right. So I don't know what the quotient is. We didn't do the division, right? But I don't care what it is because 0 times anything is 0. And 0 plus any number is that number itself. Okay. Now, the reason we like this, though, is we just defined something that we're going to be able to use moving forward. F of k equals whatever the remainder is. That's another way to write that. What is that notation? H and K was another time we used it, right? Are we using a quadratic right now, though? We don't know, right? So we don't want to use H and K because that was for the vertex, right? But what's that called, right? It's an ordered pair, isn't it? Didn't we just find an ordered pair solution of our function? We did all that. Now, keep in mind, like I said, I had to put in a specific restriction here. With this specific restriction in place, it allows me to get to this place where, hey, that's a solution of my function. Right? That means my division that I did can actually help me find solutions of a function. Now, please make sure you see here again, this is a very important restriction here. We have to use a factor that's in the form of x minus k. That's the only time this will work. Everyone follow that? So like if we scroll back here, we could say that, hey, f of 1 equals -2. Where did I get the -2 from? That's my remainder, right? So that's the remainder. Where did I get +1 from? What was our divisor? No, x minus 1 was our divisor, right? So right here is what we're looking at. What's 1 minus 1? 0. That's what would have made that factor 0, right? If I plug it in. So if we wanted to, go ahead and go plug in +1 into this and tell me what you get. Right? What's 4 minus 16? -12, right? What's -12 plus 13? +1. Right? -12 plus 13 is +1. What's 1 minus 3? -2. Right? Now, do we want to have to go through all this to evaluate a function, though? How many of you in here is like, that's one of your favorite things you've ever done? Polynomial long division. I guess that's fine. Nothing wrong with that. Now, with this said, though, how many of these on the test did I say we will have? Just one, right? So keep that in mind. Follow that. All right. The one nice thing about it's an algorithm. So that's why I said yesterday, make sure we practice. If you don't practice this, it's never going to click. You have to practice it. That's what it boils down to. All right. It's like saying you want to be an athlete in something and just expecting to show up on game day and everything's great. Is that going to work out for people? No, right? That's not how that works. And the people who thought they can get somewhere with that, at some point it catches up to them. Okay. With that said, let's put it to practice. Oh, I put those two slides on one slide, sorry. Let's put it to practice. Okay. So I have the same function here, right? Hopefully catch on that. You don't need to rewrite the f of x. What did I change? Now, technically, I can go and switch these, right? The order of the question doesn't necessarily matter, but make sure you see here, I changed the question by saying instead of 1, I did x minus 3. Does everyone follow that? Now, what that means is we can do the long division, but what remainder do we need to have to know that it is a factor? To 0, right? So to be a factor, we're looking for a remainder of 0, okay? What did I just delete here, y'all? That said solution, right? No, a 0. What I want you to see here, though, is that these two questions kind of get blended together, though. All right. Now, with that said, we could definitely do long division here, but it's going to follow a very similar pattern to what we just saw. Okay, so if you want to practice it, do the long division. Just make sure you use the other one as a kind of a guide. What you're going to see is instead of the -1, you're going to have the -3. So that'll change up some of the subtraction that takes place. What we want to do now, though, is introduce a new way to do the division. All right. This only works, though, when your divisor is in the form x minus k, which implies that, hey, for this to be true, right, that we're wanting to see when the divisor is 0. Okay. With that said, remember I did that work to show specifically we're interested in x equaling to whatever the value is. With that, with looking up here, I did x minus 3, right? If we set x minus 3 equal to 0, we'll get positive 3. That's why I used the two statements I did here. Okay. The next thing then we're going to introduce what we call synthetic division. All right. And I'll make sure to do another practice with the long division, but I want to also introduce synthetic division here because it's something that we're going to need moving forward. Synthetic division still uses the divisor and the function we're looking at here. However, we're going to write it a little bit different. Now, if you've seen synthetic division before and you have a way that you like to write it, be consistent in that. Mine might look a little different than yours. That's fine. Okay. But I like to draw my synthetic division by putting this L on its back, and I put a little box down here in the end. Why do you think I'm putting this box here? What is it that we're watching for? The remainder, right? We're doing the division, and I'm highlighting right now, this is going to be our focus a lot of times. Where's my remainder? Okay. Now, with that said, out here, I'm putting the 3. Where did I get the 3 from? That's my K value, right? Now, keep in mind, either of these questions can lead us to this 3. So make sure you see that. If I ask you if x minus 3 is a factor of this, make sure you remember, hey, I need to use the K value, not the factor itself. But if I tell you to let x equal 3, hey, I just take it as it is. If you get stuck, remember to set it equal to 0, and that's your process there. Everyone follow where the 3 is coming from? With that said, and here's where our function goes. We're not going to put variables, though. We're not putting variables. What we need to do is first ensure that we're in descending order. So we have x cubed, x squared, x3. So we're good on that end. What we can do then is just fill in the coefficients and then that constant term in the last spot. So I keep the order of what we saw, but we're not actually writing it. Just remember where we got this stuff from. That still had a place value in the sense of its term, right? The term still had an important issue, okay? So if you need to, as you saw here, I just kind of wrote it above it just to remind myself, hey, this came from x cubed, x squared, and all that. You do not need to write that there, though. But make sure you remember you didn't just randomly pick that order. So As far as this is concerned, though, we're still going to use an algorithm. What you're going to find is synthetic division is nicer because we take that algorithm that had 4 steps and we're going to break it down to 2 steps. We're going to add and then multiply. And we're going to keep doing that until we get to that remainder at the very end. Now, with that said, when you're above the line here, this is where we do the addition. But did I put anything below the 4? No. So what you're going to do is you're going to stop by dropping down the 4. Or another way to look at that, hey, 4 plus 0 is 4 because nothing was there. This is where you see now, hey, that 4 is outside with the 3. Right? The 4 and the 3 are on the outside part of this L now. So if this is going to be where I do addition, well, what does that mean I need to do with these? Multiplication. Now, what we're going to do with that, though, is say, hey, whenever I do the multiplication, that's where I'm trying to get back up. Right? And we'll say, hey, this is 3 times 4. So what number do we want to put there? And that is the process of synthetic division. I add going down, I multiply to get up. So what do I need to do at this step? Right? So my 12 is above the line, right? Right below the negative 16. So let's add those 2 things together and bring it down. So that gives us what, a negative 4? I go through this whole process again, because now I need to go back and do the multiplication. The negative 4 is on the bottom now. So I want to take that and I want to bring it back to the top. Because 3 times negative 4, as mentioned, is negative 12. Now, you don't have to put the arrows and stuff. Hopefully you're seeing I'm just putting that there to make sure to show you the path that I'm taking. It's kind of a zigzag approach. Are we good though if I put a 1 down here? All right, so with that said, then I need to get back up again. Are we good if I put a 3 here? Where am I getting 3 from? Right. Now make sure you see here, this 3 is getting repeated multiple times, right? That's where you see that, like how the factors are part of the division, right? I had to multiply everything by 3. The addition just happened to be what was there and what did I put below it, right? What do we like about the final addition, right? They cancel out, right? So what does that tell me? The remainder is 0. And that's an important part here, right? If the remainder is 0, we can answer our questions right now. Is x minus 3 a factor of f? Yes, because the remainder equaled 0. Okay. Is x minus 3 a 0 of the function? So I'm going to erase this real quick. Because it's a factor, right? We know it's a factor. I can write f of x equal to x minus 3 times my quotient. And I'm going to talk about converting that in a second, okay? But make sure you see here, this box, that's my remainder. That's the focus here at the first step. What operation do I imply when I write it this way? Multiplication. Why didn't I put anything behind it? The remainder was 0, right? So with this, if I told you to find the zeros of this function, what would you do with those 2 things that we have right here? Wouldn't we set them equal to 0? They're factors, right? Being multiplied together. I set them both equal to 0. Well, guess what? Doesn't this give me x equal to 3? Now, do we know q of x at the moment? No, but I'm going to show you how to get it, right? The division still gives me a quotient. We just have to interpret it, right? But make sure you see here, though, that we know that we have factors, right? I know then if it is a factor that yes, it is a 0. Okay, that f of 3 equals 0. Everyone follow me where we can confirm that because it's a factor, it is a 0? Now, we do have to go to that next step, though. What is q of x? All right, well, this piece down here is your quotient. Okay, what's missing, though? The x's, right? Now, remember this, though. If my divisor is just x, The nice thing about this is just remember that you ought to go through there and drop everything by 1 degree. So what's x cubed divided by x? X squared. X squared divided by x is just x. The last one, if you do x divided by x, you get a constant value. The x's are no longer there. Okay. So what you're going to see here for our quotient, we would say, hey, q of x equals 4x squared minus 4x plus 1. And that's another reason why the order of your terms is so important, because as you do that division, you should be able to go back up. Hey, where did I get that positive 4 from at the beginning? Well, I got this positive 4 from my x cubed term, so this needs to be 1 less than that, so 4x squared. We did a division there, so that's why we're dropping the x cubed down by 1. And we know this again because what did I say d of x must equal? For synthetic division to work, x minus k. Make sure you see here, this one, it got 0, right? But that's not always going to be the case. Now, what I'm hoping you're taking from this is I introduced synthetic division. So let's make sure to kind of glance over that. But at the same time, make sure you see we can answer 2 questions at one time. If something's a factor of a function, well, yeah, it's also a 0 because you can set that individual factor equal to 0 itself. This is only true, though, with what remainder? The remainder must be 0. That's the only time it works. So like make sure you compare it back to the one we did before. The remainder is -2. I cannot, it's not a factor, right? So I need to move forward and try something else sometimes. Is there any questions I clear up though with the synthetic division at this moment? All right, let's try it a couple of times. Okay. Now, make sure as you write this down that you're highlighting the 2 parts of the directions here, because it's going to be something important that as we talk about how do I use this to help me through the problem. Okay. So I highlighted the first part for you, synthetic division. The second part is going to be this thing we call the remainder theorem. These are directions that we definitely need to be familiar with. But the remainder theorem part is just a reminder. Okay. The remainder theorem is to make sure that you remember that when you go through this, that f of k equals what when we're done with the division? Huh? Is it always going to be 0 though? It's the remainder, right? Last problem, it was 0, right? But make sure you also looked at this problem here. We would say it was -2. I did this one through long division, which is fine too, right? It's the remainder theorem still works, right? You can do long division in the remainder theorem, but make sure you see here, like this would be like, oh, it's -2. That's my remainder. This one here though, the remainder happened to be 0, so it would have been 0. So this, like anytime you see the remainder theorem, just make sure you remind yourself, hey, f of k equals r. That's all that means to me. Now, again, the assumption then is that our divisor is going to be in the form of x minus k. That is the assumption that we're making here. With that said, though, as we're writing down f of x, what did someone do already, probably?
Put it in.
Yeah, make sure we put it in descending order. Nope, don't combine like terms. I don't know why I did that, y'all. Sorry. I caught it at the right time, though, right? No, I wanted us to put in descending order. So that should be 3x squared. So it'd be 2x cubed minus 3x squared minus x, and then what, plus 14? Let me make sure. Yeah, so the next one we're gonna deal with that. We're gonna deal with the combining like terms and missing terms on the next one. I wouldn't want to do that here. Now, with that said, that's my function, right? So if I go start setting up the synthetic division, excuse me. Thank you. If I go set up my synthetic division, we want to make sure we put up here 2, -3, -1, 14. I'm going to put my box right under the 14. What's the part that I need now? Right, that's my K value, right? So when you see this, we're assuming then K is 2. That's what we're going to put on the outside. All right, and that's setting up the synthetic division. So make sure you see with this problem, man. As long as I know how to do synthetic division, I'm going to get everything I need. Right? Most of the work here is going to be the fact that you use the synthetic division. And I will tell you right now on the test, when we take the test, when we take the final, if it says use synthetic division and the remainder theorem to find the following, and you choose to do something else, you will get 0 points. You must use synthetic division. I'm going to hold true to this one because I need to see that you know how to do the synthetic division and interpret it from the first step that we need. Because moving forward, as I hinted at, we're going to focus on remainders of 0. But that's not the only way we use synthetic division. With that said, what do? Bring down the 2, right? Once we get below that bar, what operation? Right, so below the bar is multiplication, above the bar is, the nice thing here, I hope you're seeing, is once you stack them, hey, they're right there with each other. That's kind of more how we used to write our addition all the time, right? Be careful with your signs though, of course, as we go through that. Is there any concerns with where I'm getting these values from? Now, when you watch videos online, if you choose to do that, they're not always going to write synthetic division the way I do. So just keep that in mind. I know some people use more of this approach, which is perfectly fine. If you write your synthetic division differently than me, that's fine. It's whatever you want to do there. Okay. I personally started doing this to make sure to help students emphasize what is it that we're typically trying to find. Right, this makes a good separation between what we're going to use as far as the quotient is concerned and as far as the remainder is concerned. That's the main thing we need to start with, is knowing where to find the stuff. So if I ever asked you to, you could give me the quotient, but did I ask for the quotient here? No, I asked you to identify what? The remainder, right? That's what the remainder says, is identify the remainder. But the way we want to write this is that f of 2 equals what? 16. That is a solution of this function. You don't believe me? In your calculator right now, plug in 2 into f of x and tell me what you get. Plug 2 into that function, you'll get 2 times 8, which is 16. 3 times 4, which is 12. It's a negative 12 though, right? Negative 12 minus the 2 that follows it is negative 14. Negative 14 plus 14 is 0. That means all that we have is 2 times 8. And what does 2 times 8 equal? So there we go, right? But synthetic division will take probably 10 seconds less at least than the calculator would have taken you. All right, so please keep that in mind, that synthetic division is longer. And if you think that 10 seconds isn't a big deal, wait till we get to the problem on the next slide where we're not going to do it once, but we may have to do this 5 or 6 times. All right. So we have to understand that this is something I can tell you right now when it comes to the test. If you choose not to do synthetic division, it's not going to work well for you. Okay, it will not work well for you. This is definitely something we have to get comfortable with. What I hope you see, though, the synthetic division is a little bit nicer than the long division itself. The issue is that we have to remember, though, is that it only works whenever my divisor is in this form. Nothing's in front of x. The coefficient of x is 1. The constant is some rational number, though. The constant can be any rational number. but the x has to have a coefficient of 1 and there's no exponent on it, right? So it only works for this particular linear term. Okay, so please keep that in mind. Now, with that said, let's do the second one. What do you like about g of x, though? Already in descending order, right? Now, make sure to throw out some stuff right here. Could we factor that by grouping if we wanted to? Does 9 go into 54? How many times? 6 times, right? So we could factor this one, right? So we could do that to even confirm what's going on here, right? But let's do the synthetic division and see what happens. Oops. We go with the setup. Is there any concerns there? Now, before I go do this one, make sure you see here that like my focus today, we're going to do more with the quotient as we go forward. As I showed you on the first one, I kind of made sure to show you where the quotient was. I want to make sure we understand where the remainder is and why that definitely is something we want to focus on. Okay. Remember, that's going to be this value here, right? So whenever you go over here, we're trying to find f of k equal to r, right? So that means my k value will be whatever that is. And that goes back to just that remainder theorem perspective, okay? With that said, though, no questions were asked last time, so let's go through this. It's a little bit different this time, right? Are we always going to get a remainder of 0? No, more often than not, we're not going to get a remainder of 0, but I just did this and look at that. We get a remainder of 0. Now, make sure you see here what I wanted us to do for this problem is to write that as g of -3 equals 0. Now, if we take what we previously did, we should hopefully recognize that means that -3, right, is a 0 of the function, but also that x minus 3 is a factor of the function. Okay. With that said, if I factor this by grouping, so let's zoom in real quick, -6, -9. If we try factoring by grouping, we're able to actually factor this, okay? What's going on here that agrees with us finding that x minus 3 is a factor? Right. The square root of 9 is 3, right? Good. Where we could rewrite this as x minus 6 times x plus 3 times x minus 3. And there's our confirmation, not what's wrong with it. This is our confirmation that what we just found is true from a factoring perspective. Okay. Now, I didn't tell us to do that. I just want to make sure to show that that would be kind of another perspective we could use here. It's not always going to work though. Any concerns with the synthetic division or the remainder theorem, how I just took whatever I used and said that's going to be a solution of the function with the remainder is the y value. And if you ever get stuck there, that's where this comes into play here, right? That's why I changed the division into multiplication, right? I forced the divisor to be something specific so that I can use this to my advantage. That's the whole focus there, that, hey, by using that divisor, I know that that equals 0. And 0 times anything is 0. And 0 plus r is just r. That's where I got that from. By forcing my divisor to be x minus k, I can now evaluate the function using division. Okay. With that said, let's look at it from this function. What in the world would I do with it here? Now, this is going to be more of me just kind of giving a walkthrough of why it's helpful. Okay. we're gonna do, like I said, we're definitely gonna do more with this stuff. This is just me giving us kind of like, okay, how can we highlight its purpose? Why would we want this? First and foremost, make sure you saw in the previous two, I said those were specific situations, use synthetic division and give me the solution you just found. So I can tell you to evaluate a function using synthetic division, and that's what we want to do. Now, what I usually do on the test, though, is I will write it the same way. I will say, hey, evaluate this function using synthetic division and the remainder theorem. The remainder theorem is your hint that, hey, when I do this, f of k equals my remainder. That's the hint there. Right now, though, I don't want just any remainders. What am I asking us to find? Zeros. All I care about is h of x equal to 0. That's all I want here. Okay. What do I use for the division, though? Can't factor this one by grouping. Why can't I use grouping here? The 24 and 45, they don't really, they have a 3 in common, right? But that's never going to give us 22, right? There's nothing I can do here. You could try grouping. It does have 4 terms, but you're going to find it's not going to work, right? This is where synthetic division comes in. Now, with that said, please understand, even synthetic division will not be guaranteed to work. Okay. But as we deal with these functions, we need to go back to some of the stuff we talked about. Why would I highlight this term? Fourth power. What does that mean to us? 4 answers. Or what we started saying with this test is, hey, this is a degree 4 polynomial, right? I know that I should have 4 different solutions here, right? I should say 4, not 4 different, but I should have 4 solutions. Multiplicity can change that, of course. We can get the end behavior from that. Do we need the end behavior right now? No, we could talk about that though. The degree 4, though, I feel is definitely important as far as 4 solutions. Why then would I highlight this though next? That's my constant term, right? One thing hopefully you remember from that is, hey, h of 0 is 45. That doesn't help me right now, but that would hopefully be something you jump to right away. Now, make sure you also see here, if I have a bunch of factors, right, shouldn't those factors still multiply to 45? Like if I wrote this out, could I have something like x squared minus 3 times x squared plus 7? Would that even work? No, right? Yeah, x squared times x squared gives me x4, but what's 3 times 7? 21, right? They better still multiply to 45, right? So yes, the 45 is helpful as far as getting that y-intercept, but it's going to help me in the factoring part here. What you're going to find is when you need to find zeros of a function, and those factoring skills that we've discussed in the past do not help you. So there's no GCFs, right? It's not a trinomial. It doesn't work with factoring by grouping, right? So those are our 3 main ones, and it's not one of those special ones. Don't forget about the special ones, right? As we just saw in the previous problem, a squared minus b squared, or a cubed and b cubed, right? The cubic can be sum or different, so it doesn't matter sign. Those are some special ones to make sure, again, that we watch for, okay? If none of those things work, this is where then we say, okay, let's try synthetic division. Everyone follow that? Now, the only numbers we want to use here are going to come from these 2 terms. Okay, this is where we're going to talk about possible rational zeros. And I'll make sure to expand this some more. That's why I just quickly showed you that, like, hey, 3 times 7 will never work, right? Because I need to be 45, not 21. Okay, so make sure you see that what we want is factors of 45, but also that leading coefficient matters too. So this will be your constant term. This will be your leading coefficient. Both of those will help us here as well. Okay, my leading coefficient is 1 though.
That plus or minus?
Yeah, plus or minus 1. Because what's -1 times -1? Right? What's negative 5 times -9? Right? So the sign isn't matter as long as we match it up to get to what we need. Okay, that's all we're saying. With that said, though, what are factors of 45? 1 and 45, right? 5 and 4, does 2 work? No. 3 and 15, right? Oops, forgot my plus or minus signs, y'all, sorry. We already said 5 though, right? Oops, sorry, skip the 9. I think we can be confident with that list there, right? Now, I listed this one differently though, because remember here, I'm just trying to say, what are the numbers that even possibly could work here? That means I could do synthetic division with any real number I can think of, but is it going to help me? No, we don't want to do that. We don't want to just start with 1 and work our way through 100 just to see if any work, okay? So what I did is I focused on the values that the problem gave me, right? To build a list that just tells me, hey, of any number that's going to work, these would be the rational numbers that could work. Now, keep in mind, is the leading coefficient always going to be 1? Oh, so we probably have some fractions sometimes, right? So keep in mind some fractions will get involved. Now, with that said, does that mean any of these are going to work? None of these could work. Is that clear to everyone? If none of them work, guess what? That's where, again, we have to go that step up, right? What's going on, say, from a perspective that calculus gives us. That's not what we're focused on, right? So with this class, guess what? At least one of them better work, right? So with that said, what number y'all want to start with? 3. Let's start with 3. If 3 works right away, then what was the point in listing all of them, right? But make sure you see here, I'm putting the 3 on the outside. We're just trying to see if 3 works, right? We'll know if 3 works if we get what? A 0 from my remainder, okay? Now be careful here. What's going on with h of x that's a little bit different than the previous two? X to the 4th, right? What goes after the 4th? Doesn't an x cube supposed to follow x to the 4th though? So this is where we have to put that 0, right? We have to put a 0 here. This is gonna be one thing that's definitely a little bit different because like when we think about numbers, if I gave you 1042, we just naturally put the 0 there. Polynomials, if it's 0x cubed, we just don't put it. So we have to make sure to remind ourselves, wait, I need every term present for synthetic division to work. So in this case, make sure you catch that. That's one difference though, as we deal with synthetic division that we have to watch for. There was no x cubed, so I'm going to put a 0 in place of it. I can then move through this and put the rest of those numbers. All right. Now, are we okay with where the 0 is coming from? I haven't had any concerns with the synthetic division, so let's get through it. Because what you're going to find here, this is just, hey, let's do it. Let's get it done quickly. If you get stuck on numbers, this is a great place to have your calculator out to help you with the addition, subtraction, and all that, because it's kind of just a repeated step, right? Hey, 1 times 3 is 3. Bring it down. 3 times 3 is going to be 9. If it's stuck here, your calculator can do it for you, right? That's the nice thing about it. Was what, negative 13? No.
Negative 13.
It is 13?
Yeah, and then it's 39. Negative 39.
Which gives us negative 15. Why did you already do this?
No, I'm just like that for real.
Some people, I always have a student that I genuinely feel they guess. But I can't show the guess and check part when you pick the right one right away. Nothing wrong with that though. All right. But does everyone see here that using the remainder theorem, we got something that's useful? We now know that h of 3 equals what?
0.
Equals 0. Okay. Now, is that all of the zeros of h? No, because Daryl, you said how many should we have? 4 zeros, right? We should have 4 zeros to this problem. So right now we only found 1. We need to keep going on to find the other ones. Okay, so keep that in mind. Are we good though with this synthetic division here for the first one? All right. Now, what we're going to have to do here though is we're going to have to rewrite this problem. First and foremost, we need to recognize that we just found x minus 3 is a factor. Okay, so make sure you catch that. Where we talked about this statement here, this is another way to write that. If it's a 0, we know that x minus k is a factor. Okay. With that said, then the next piece here, I need the quotient. This is gonna be my quotient, okay? So just make sure you remember, go back to, as I gave an example earlier, look up to what you're working with and go down by how many degrees?
One.
Just one, right? So x to the fourth becomes x cubed. Then we have x squared, we have x, and then we have our constant term. But make sure you see here, like those don't have the variables, but that's where this comes in to help us with that. Everyone okay with that? Now, do we have any missing terms this time? No, so we don't have to worry about it. Will factoring by grouping work here?
Yes.
We could try, it's 4 terms, right? But what do 13 and 15 share in common? We're only gonna be able to pull out a -1, right? Is that gonna help me with a 3? No, right? So you can you could go write it out if you need to, right? If you need to write it out, write it out. But we can see here, this grouping's not gonna work. So I have to continue with this, right? Through synthetic division, okay? Now, the good news is, do I need to go back to h of x to keep doing that? No, right? We have a quotient that allows us. What do we like about this quotient here that makes the synthetic division a little bit nicer? What do we notice about the 2 terms that we're supposed to focus on? Did the leading change? Did the leading coefficient change? Oh, it was 1, it's gonna stay 1, right? And it shouldn't change. When doing synthetic division, the leading coefficient better not change. What did my constant do though? Went from 45 down to 15. These are the possible rational zeros of 45, right? But this is where we just found I no longer have to worry about some of these. Does everyone see that? Now, I didn't know that from the beginning. You could have tried 9, -9, 45, and -45, but guess what? They wouldn't have worked. How do I know this from my perspective? Well, hey, look, they better be factors of 15 now, right? Like I showed you earlier with 7 and 3, the same thing is true here. I can't use 9 anymore because 9 doesn't divide into 15 nicely, right? With that said, then, is what we want to do here is make sure to use this new list to continue on. What number do y'all want to try now out of the list that we have? Let's try 5. Is 5 going to work again?
I hope.
Now, be careful here. Let me make this zoomed in a little bit. What am I doing? Now, make sure you understand here, I'm focusing on this quotient now, okay? So y'all said to try 5. I'm using the quotient now, though, not the original function. There's no need to go back to the original function. We've already picked some of it off to make it a little bit nicer. This doesn't look good at all. Not that my handwriting ever looks good. All right. Make sure you see here, I took the values from the quotient exactly as we saw them, and I'm copying them in here because I don't need to go back to the original function again. Right? You should always use the quotient moving forward. Well, let's run through this. I thought you said it was going to work.
I didn't say that. I said.
Why'd you pick 5 then?
I
I trusted you.
Oh, you want me to? You got mad at me when I put 5.
Does 5 work?
Mhm.
No. So should I try 5 again?
No.
No. What's another number then we can use?
3.
Now keep in mind when you do that, well, that means positive 5 will never work. So make sure you scratch that off that like, hey, 5 will never work. Okay. You said what?
She said 1.
What number? You want to try 15? Let's try it. Now, okay, before I try 15, what was the issue here with 5?
But
It was always positive, right? So what's going to happen if you try 15?
1.
You see how it's only going to get bigger than 5? So I would encourage you to say that, like, hey, try to pay attention. Like I mentioned, this stayed positive the whole time. 15 is definitely not going to work. Trying 1 or 3, We'll see what happens.
Let's try one.
Let's try one.
So do we, are we doing?
Huh?
So like, even if it doesn't, so we only use. never mind.
Yeah, focus on the quotient, because once you get one factor out, you don't want to go back to the beginning. The problem is though, that what you will run into and why we need to use the new one, and I'll make sure to share later, is that word multiplicity. Remember, multiplicity says that two solutions can be the same value. Synthetic division will not show you multiplicity. That's why you have to use the quotient. Huh?
It's still not.
It's still not working? You sure?
Oh,
No, it definitely didn't work. Did you already do it? Did it work? All right, so let's slide this over. Are we catching though? This is a guess and check situation, right? Personally, I would have picked 3 again just to see. It worked one time, maybe it'll work again, right? You said -5 though, then make sure I use the
so we
same
can
thing.
use negatives?
Yeah.
Oh.
Remember what I said at the beginning though, was that when you see +45, remember you could have -5 times -9, right? So negatives can be used. The key is it better multiply to 45. Oops, as I write 45. Now, like going back to when you were saying 15, like the fact that none of those became negative, well, let's try -5 and see what happens, right? That would have been a great transition. You said 5. Why am I doing -3? I'm sorry. I'm like, what? -3 was one of our numbers, but you said -5. So let's make sure we use -5. And there we go. All right. So we found that Q of -5 also equals 0. Now, as we go through this, there are different things. So like the cart has a thing with signs, right? As far as the signs on the coefficients and how that can help us, okay? I feel for us right now, the best approach is just kind of take that guess and check approach. Is at the very least, make sure you know where we got these rational zeros from. That's the most important part. Make sure you see that just as we did with factoring quadratics, we focused on, the first term and the last term, right? So we're taking that same kind of approach. Now, with that said, though, let's make sure we kind of keep what we have going on real quick. What you want to do is make sure you keep track of what you found. So from our first division, we used what? 3. And we got x cubed plus 2x. No, 3x squared, sorry. Minus 13x minus 15, correct? From that second one, we did -5, right? So we had the x minus 3, don't lose that, it's still there. -5 we'll write as x plus 5. And what did we get? X squared, was it minus 2x? Yep. Minus 2x minus 3. Okay. Now what you'll see here is that we did it twice and we found 2 different numbers that work. Okay. Also make sure you go back and you compare how I got this one to how I explained how I got this one. We'll practice this more, okay? So keep that in mind. But when it comes to dealing with this, make sure you also see that we're going to get to a place where we can start using things that we have practiced. So, hey, this is quadratic now. So let's make sure we use that process that we've talked about in the past where we have A times C and B. We could then say -3 times 1 and -3 plus 1. Both of those things work. With that in place, I could factor my polynomial down to x minus 3, x plus 5, x minus 3, x plus 1. If you need to use grouping there, of course, use whatever you need to. My main focus was always that table to show that we could factor that quadratic. With that said, a quadratic, if we can't factor it, what should we use? The formula, right? So don't forget about that. That is important because here I told us to find the zeros, right? So if you can't factor it, then we need to go to the quadratic formula to get my zeros. Right now, if we get cubics that we're stuck on, that's a whole different story. But once we get to quadratic, we know how to get to the zeros even when we can't factor. We didn't need it here though. What do we notice about my factors though, as we finish up? Right, so we found these two from synthetic division, right? This just happened to be something that we were able to factor from the quadratic. But what we want to make sure to do is that whenever we see repeated factors, that we write it using an exponent. So we should have picked 3 again. If we would have tried 3 again, it would have worked. That's what that means. Okay. Now make sure you see here too, as far as finding the zeros, what we would conclude then is x equal to 3, x equal to -5, which we found from the division, but my last zero that we get then would be the -1. Okay. Now, please understand, we will go into this more. This was me just making sure to show us how to use synthetic division. And this last one is just walking through an example with you where we can see where it's helpful. If we had to do long division 4 times, it would have taken an entire hour-and-a-half class for those long divisions, right? So keep that in mind. That's why synthetic division is very helpful. If you went in and started plugging those numbers into the function, right? Know that that's going to take you over twice as long to get done by plugging in 3 into h of x and then working it out on calculator by hand. It's going to take longer, okay? Even if you have a calculator, you can quickly check each value. It takes longer. That's, again, why synthetic division is definitely something we need to have. The last thing I will say as we finish up, you must use synthetic division on one of the problems. All right, this is going to be, as you saw here, I will say something like evaluate the function using synthetic division and the remainder theorem. So make sure that you look at these 2 examples and kind of highlight them in your notes that if for the test, as well as the final exam, this is something you will be asked to do. So we need to keep that in mind. Any questions as we finish up? All right, then have a good day and I will see you all tomorrow.